Welcome student, this is video of MCQ of Group Theory Part 2. Dear friend, first subscribe my YouTube channel PV Patil and share to our friend. First MCQ, which of the following is a improper subgroup of group G? Which of the following is a improper subgroup of group G? Answer is option B, G. G is improper subgroup of G. Answer is option B. Second, which of the following is travel subgroup of G? Travel subgroup means zero subgroup means identity subgroup. Answer is option A, single element identity. Third one, a subgroup H of a group G is called dash if H is not equal to G. H is subgroup of G and H is not equal to G, then H is proper subgroup. If H equal to G, then it is improper subgroup. Now H is not equal to G, then this is a proper subgroup. Answer is option C, proper subgroup. 4. The number of proper subgroup of the group Z plus R. Z set of integer, operation addition, then number of proper subgroup of Z plus R, infinite many. Answer is option D, infinite. 5. The number if proper subgroup of group Z modulo 12 addition R. See here, Z modulo 12 is a set containing element 0 bar, 1 bar, 2 bar up to 11 bar. Therefore, proper subgroup of Z modulo 12 R 0 bar. Group generated by 0 bar is equal to group containing single element 0 bar. Second one, group generated by 2 bar is equal to group generated by 10 bar is equal to group containing element 0 bar, 2 bar, 4 bar, 6 bar, 8 bar, 10 bar. Group containing element 0 bar, 2 bar, 4 bar, 6 bar, 8 bar, 10 bar. Now the group generated by 3 bar or group generated by 9 bar is equal to group containing element 0 bar, 3 bar, 6 bar, 9 bar. Now group generated by 4 bar means group generated by 8 bar is equal to group containing element 0 bar, 4 bar, 8 bar, and last one group generated by 6 bar equal to group containing element 0 bar, 6 bar. Means there are 1, 2, 3, 4, 5 proper subgroup. Answer is option C, 5. Number 6. Which of the following is subgroup of a group G containing element 1, minus 1, I, minus I under usual multiplication? This is a group G. Then which is subgroup of this group G? 1I is not a subgroup. Minus 1 minus I, this is also not subgroup. I minus I, this is also not subgroup. 1 minus 1. 1 minus 1 is subgroup of group G. Answer is option D, 1 minus 1. 7. Which of the following is not a subgroup of group Z plus? Set of integer, operation addition. Which of the following is not subgroup of this group Z plus? This set of all even integer. Set of all even integer is subgroup of group Z plus. NZ for any n belong to natural number. So NZ is a subgroup of group Z plus. So single element 0 is subgroup of group Z plus. But set of all odd integer. Set of all odd integer is not subgroup of group Z plus because set of odd integer does not satisfy condition of group. Addition of two odd integer is a even integer. This is not belong to this set in odd integer. Therefore, answer is option C. This set of all odd integer is not subgroup of group Z plus. 8. Intersection of any two subgroup of a group is. Intersection of any two subgroup of a group is subgroup. Answer is option C, subgroup. Intersection of any two subgroup is subgroup. 9. Consider the statement. First one, union of two subgroup of group G is subgroup of G. union of two subgroup of group G is subgroup of G. This is not a correct statement. Intersection of two subgroup of group G is subgroup of G. This is a correct statement. A is only statement 1 is correct. No, statement 1 is incorrect. Only statement 2 is correct. Yes, second statement is correct. This is right answer. Option C, both the statement are correct. No, wrong. Statement 1 is incorrect. Statement 2 is correct. None of the above. Answer is option B, only statement 2 is correct. 10. The necessary and sufficient condition for non-empty subset H of a group G to be subgroup is that the non-empty subset H of a group G is subgroup if AB belong to H, which imply that AB inverse belong to H. This is a correct answer. AB belong to H imply that AB inverse belong to H, then H is subgroup of G. AB belong to H imply that A plus B belong to H. No, this is wrong answer. A belong to H imply that A inverse belong to H. No, this is not a sufficient answer. AB belong to H imply A into B belong to H. This is also not necessary and sufficient answer. So answer is option A. AB belong to H imply that AB inverse belong to H. 11. If 2Z plus and 3Z plus are two subgroup of a group Z plus, set of integer addition is a group and 2Z and 3Z are subgroup of group Z plus, then 2Z union 3Z is, this is not a subgroup. 2Z union 3Z is not a subgroup of group Z plus. Answer is option A, not subgroup of group Z plus. 12. If H and K are subgroup of a group G, if H and K are subgroup of a group G, then H union K is subgroup of G if H union K is not a subgroup, but H union K is subgroup of G if some condition are satisfied. First one, H is subset of K or K is not subset of H. No, this is wrong answer. H is subset of K or K is subset of H. This is the correct answer. Option B is the answer. H is subset of K or K is subset of H, then H union K is subgroup of G. 13. Every cyclic group is abelian. Answer is option B, abelian. 14. Every subgroup of a cyclic group is cyclic. Answer is option A, cyclic. 15. If H is subgroup of group G and A belong to G such that HA equal to H, then A belong to H, Answer is option B, A belong to H. 16. The number of generator for the group G is equal to 1 minus 1 I minus I under usual multiplication R. The number of generator for the group G is 1 minus 1 I minus I under usual multiplication R. Number of generator are only 2, 1 and minus 1. The group G is 1 minus 1 I minus I under usual multiplication is generated by plus 1 and minus 1. This group is generated by plus 1 and minus 1 means generator are only 2. Answer is option B, 2. 17. Which of the following group is not cyclic? Group G is equal to containing element 1 minus 1 I minus I under usual multiplication. This is a cyclic group generated by 1 and minus 1. Now set of integer modulo 6. This is also cyclic group. Option D is Z plus set of integer addition. This is also cyclic group. But Z dash modulo 8 multiplication is not a cyclic group. Answer is option C, Z8 dash multiplication 8. 18. Which of the following group is abelian but not cyclic? Group G containing element 1 minus 1 I minus I under usual multiplication. This is a cyclic group generated by 1 and minus 1. Z modulo 6 is also cyclic group. Set of integer Z plus is also cyclic group, but Q plus, this is not a cyclic group. Set of rational number operation addition is not a cyclic group. So answer is option C, Q plus. 19. Let H be subgroup of group G and A belong to G. Then the set H such that H belong to H is known as set H such that H belong to H is known as left coset of H by A. Answer is option A, left coset of H by A. 20. If H is subgroup of a group G and AB belong to H such that AH equal to BH, then AH equal to BH, then B inverse A belong to H. This is wrong answer. B inverse A belong to H. This is correct answer. Answer is option B, B inverse A belong to H. 21. The number of distinct left coset of a subgroup H. Number of distinct left coset of subgroup H is 1 minus 1. In the group G, 1 minus 1 I minus I under usual multiplication R. Number of left coset of subgroup HR. Left coset of HR 1H. 1H is multiplied by 1, so 1 minus 1 is H set. Minus 1H is multiplied by minus 1, so minus 1 and plus 1 is H, again H set. IH is I minus I, and minus IH is minus I plus I is IH, means number of distinct left coset are H and IH, means there are two distinct left coset. Or we can also solve this problem by using Lagrange's theorem. Index of H in G is IGH is equal to, IGH is order of G divided order of H. Order of G is 4 and order of H is 2, so 4 upon 2 is 2, means two distinct left coset. Answer is option B, 2. 22. If H is subgroup of a finite group G, if H is subgroup of a finite group G, then order of H divide order of G. This is statement of dash theorem. This is statement of Lagrange's theorem. Answer is option C, Lagrange's. 23. If H is subgroup of a finite group G, if H is subgroup of a finite group G, then dash order of H divide order of G. Answer is option A, order of H divide order of G. 24. If N belong to N and A belong to Z such that AN is equal to 1, A and N are relatively prime, the GCD of A and N is 1, then A raised to phi N is equal to 1 mod N. This is statement of dash theorem. This is statement of Euler's theorem. Answer is option A, Euler's theorem. 25. If P is a prime number and A belong to Z, P is a prime number, A belong to Z such that P does not divide A, then A raised to P minus 1 is congruent to 1 modulo P. This is statement of dash theorem. This is statement of Fermat theorem. Answer is option B, Fermat theorem. 26. Let G be a finite group and A belong to G. Let G be a finite group, A belong to G, then A raised to order of G is equal to dash. A raised to order of G is equal to identity, means answer is option A, E. 27. Let phi n be an Euler's totant function, then phi 10 is equal to dash. Euler's function phi of n to n defined by phi n is equal to the number of positive integer less than or equal to n and relatively prime to n. 1, 3, 7, 9 are positive integer less than or equal to 10, and all these numbers are relatively prime to 10 because GCD of 10 and 1 is 1, GCD of 10 and 3 is 1, GCD of 10 and 7 is 1, GCD of 10 and 9 is 1. Therefore 510 is equal to 1, 2, 3, 4. These are 4 number. 510 is equal to 4. So answer is option C, 4. 28. Let phi n be an Euler's totant function, then phi 17 is equal to. If p is a prime number and phi n is Euler's function, then phi p is equal to p minus 1. If n is prime number, then phi p equal to p minus 1. Here 17 is a prime number, so phi 17 equal to 17 minus 1 and is equal to 16. So answer is option C, 16. 29. The remainder obtained when 3 raised to 54 divided by 11 is dash dash dash. 3 raised to 54 divided by 11, then find remainder. Solution. Here 11 is a prime number and 11 does not divide 3. 3 and 11 are relatively prime, means their GCD is 1. Now we know Fermat theorem is if p is a prime and p does not divide a, then a raised to p minus 1 is congruent to 1 mod p. A raised to p minus 1 is congruent to 1 mod p. Here p is equal to 11 and a is equal to 3. So p is a prime number, 11 is prime number and 11 does not divide 3. Therefore, by Fermat theorem, 3 raised to 11 minus 1. 3 raised to 11 minus 1 is congruent to 1 mod 11. 3 raised to 11 minus 1 congruent to 1 mod 11. So 3 raised to 10 is congruent to 1 mod 11. So taking raised to 5 of both sides, therefore 3 raised to 10 raised to 5 is congruent to 1 raised to 5 mod 11. So 3 raised to 50. 3 raised to 50 is congruent to 1 mod 11. Now we require 3 raised to 54. We get 3 raised to 50. Now require 3 raised to 54. So require 3 raised to 4. Now we know 3 raised to 4. 3 raised to 4 is 81. 81 mod 11. 81 mod 11. 11 sevens are 77. 81 minus 77 is 4. So 81 is congruent to 4 mod 11. So therefore 3 raised to 50 into 3 raised to 4. 3 raised to 50 into 3 raised to 4. Product of these two terms is congruent to 1 into 4 mod 11. So 3 raised to 50 into 3 raised to 4 is 3 raised to 50 plus 4 means 3 raised to 54 is congruent to 4 mod 11. So remainder when 3 raised to 54 is divided by 11 is 4. Remainder is 4. So answer is option D, 4. 30. The remainder obtained when 5 raised to 10 minus 3 raised to 10 is divided by 11 is dash dash dash. Fermat theorem, if p is prime number and p does not divide a, then a raised to p minus 1 is congruent to 1 mod p. Now here for the first term, 11 is a prime number and 11 does not divide 5. For 5 raised to 10 divide by 11, 11 is prime number and 11 does not divide 5. So by Fermat theorem, 5 raised to 11 minus 1. 5 raised to 11 minus 1 is congruent to 1 mod 11. So 5 raised to 10 is congruent to 1 mod 11. We get the value of 5 raised to 10 is 1. 5 raised to 10 is congruent to 1 mod 11. Similarly, find 3 raised to 10. Again, 11 is prime number and 11 does not divide 3. 11 is prime number, 11 does not divide 3. So by Fermat theorem, 3 raised to 11 minus 1 is congruent to 1 mod 11. 3 raised to 11 minus 1 is congruent to 1 mod 11. 3 raised to 10 is congruent to 1 mod 11. And then their difference 5 raised to 10 minus 3 raised to 10. Therefore 5 raised to 10 minus 3 raised to 10 is congruent to 1 minus 1 mod 11. So 5 raised to 10 minus 3 raised to 10 is congruent to 0 mod 11. Means remainder is 0. Remainder when divided by 11 is 0. Answer is option A, 0. 31. Every proper subgroup upper group of order 55 is dash dash dash. Group of order 55, find its proper subgroup. Proper subgroup upper group of order 55 are of order 1, 5 and 11 because factor of 55 are 1, 5 and 11. For group of order 1, it is a travel group, so it is cyclic. For group of order 5 and 11, we know 5 and 11 are prime number. Also, every group of prime order is cyclic. So 5 and 11 are prime number. So these two groups are cyclic group. So proper subgroup of order 1, 5, 11 are cyclic. So answer is option C, cyclic. 32. The number of cyclic subgroups of a group of order 41 is equal to dash dash dash. Number of cyclic subgroup of a group of order 41 is equal to dash dash. 41 is a prime number, so divisor of 41 are 1 and 41 only. Factor of 41 are 1 and 41 only. Also every group of prime order is cyclic. Therefore there are two cyclic subgroup, single element identity and itself. Single element identity and itself. Because group of order 41 is itself and single element identity is group of order 1. So answer is option C, 2. 33. If G is cyclic group generated by A, G is a cyclic group generated by A, then A inverse is dash dash dash. A inverse is also generator of G. So answer is option B, generator of G. 34. A function f from G star to G1 star dash. A function f from G star to G1 star dash is called a group homomorphism if f of A star B, f of A star B equal to f of A star dash f of B for all AB belong to G. Answer is option B, f of A star B equal to f of A star dash f of B for all AB belong to G. 35. If f of G star tends to G1 star dash is group homomorphism and E1 are identity elements in G and G1 respectively, then f of E is equal to E is identity in G and f of E is identity in G1. Identity in G1 is E1, so f of E is equal to E1. So answer is option C, E1. 36. If f of G star to G1 star dash is a group homomorphism, then the set X belong to G such that f of X equal to E1 is identity in G1. E1 is identity in G1. X belong to G such that f of X equal to E1 identity in G1 is dash dash dash. This set is kernel of F. Answer is option B, kernel of F. 37. If f of G to G dash be group homomorphism and H equal to X belong to G such that f of X equal to E dash. E dash is identity in G dash, then H is dash dash dash. We know H is kernel of F. Also H is here subgroup of G. H is subgroup of G. Answer is option A, subgroup of G. 38. If f of G to G dash be a 1, 1 and 2 and group homomorphism, then F is 1, 1 and 2 group homomorphism, so F is isomorphism. Answer is option B, isomorphism. 39. Every finite cyclic group of order n is isomorphic to. Every finite cyclic group of order n is isomorphic to option B, Zn plus. Answer is option B, Zn plus. 40. If f of G to G1 is a group isomorphism and A belong to G, f of G to G1 is a group isomorphism and A belong to G, then first option order of A less than order of f of A. No, wrong. Order of A greater than order of f of A. This is also wrong. Order of A equal to order of f of A. This is correct answer. Answer is option C. Order of A equal to order of f of A. 41. If G is cyclic group with generator A, G is generated by A, then the homomorphic image f of G is equal to, means homomorphic image f of G is generated by f of A. Answer is option B, generated by f of A. 42. If f of G to G dash be group homomorphism, f of G to G dash be group homomorphism and kernel f equal to single element identity, then f is 1 1. Answer is option B, 1 1. 43. Let R plus is a group of real under addition. R plus is a group of real under addition and f of R to R defined by f of x equal to 3x for all x belong to R, then f is group homomorphism. S, correct answer. Then answer is option A, group homomorphism. 44. Let R plus is a group of real under addition and f of R to R defined by f of x equal to phi x plus 1. F of x is phi x plus 1 for all x belong to R, then f is first option, group homomorphism. No, wrong. Phi x plus 1 is not a group homomorphism, means answer is option B, not group homomorphism. Answer is option B, not group homomorphism. 45. Let G is a group A belong to G and f of G to G defined by f of x is equal to Ax A inverse for all x belong to G. F of x equal to Ax A inverse for all x belong to G, then f is automorphism. Answer is option B, automorphism. Dear friend, subscribe this channel and click on bell icon. Thank you.